Here's another problem with the distributed load. So we see you have this gray bar right here, A to B, and we have a loading curve that changes, right? First it's just constant at 800 newtons per meter, and then it linearly increases from 800 newton per meters to 1.6 kilonewton per meter, so 1600 newton per meter. All right, and we of course want to find what the total resulting force is and where it acts. So we could find out what the mathematical equation for this and then do all the integrations, but of course with these simple shapes we can just cut this into two simple easy shapes to handle, right? So I would suggest we do a cut right here, right? So we call that 1, and this we'll call 2, right? It's a rectangle and a triangle, and we know how to deal with rectangles and triangles. All right, so if we want to get the resultant force for the rectangle, R1, right, then we know that is just 2.5 plus 2.5, so 5 meters. And the loading is 800 newtons per meter, distributed load, 800 newton per meter. So that will give us 4,000 newton or 4 kilonewtons. That was my resulting force from the rectangle. And then for the triangle, R2, the area of a triangle is just 1/2 times the length, which is 2.5 meters, times the height. Now we're going from 800 to 1600 kilonewtons, so that would be a height of another 800, or maybe we'll just write it like this: 1600 newton minus 800 newton, to make it very clear. And if we plug that in, right, that's 800. 800.2.5 divided by 2 in the end gives me 1 kilonewton. That'd be my R2s from the triangle. Now to the total. R is just going to be R1 plus R2. So 4 kilonewton plus 1 kilonewton is 5 kilonewton. Right, so I know that the resulting force of this loading here would be exactly 5 kilonewton. All right, now if I want to find where the location is, then again I have to get all the moments and divide them by the total force we just calculated. So let's get our moments. So if I say M1, right, we know we have our R1 would be somewhere here, right? It's a rectangle, so the centroid is halfway along. So that means I would get R1 times 2.5 meters. R1 was 4 kilonewton, so 4 kilonewton times 2.5 meters, and that gives me 10 kilonewton meters. That's my 1. Now my 2 would be somewhere up here. R2, right? That's a triangle, so we know that's 2/3 in, so I can say my M2 is equal to R2, which was 1 kilonewton. And now the moment arm, right? You have to remember that we're counting all the way from over here. Right, that's where our X starts. So we have to do 2.5 meters to get from here to where my triangle starts. And then remember that my triangle is 2/3 in, right? That's where my force, or where my centroid is. So it'd be 2.5 plus 2.5 meters times 2/3. And with that I get, that gives me 26 over 3 kilonewton meter. So then my total MR. It just fits up out there. My total MR would then be 10 kilonewton meters plus 25 over 3 kilonewton meters. That would be 25, somewhere I have a mistake here, 25 over 6, I'm sorry. 25 over 6, not over 3. I'm getting ahead of myself there with the numbers. Down there. Oh, because I have the 2.5, so I'd have to do another. Okay, that makes sense. All right, so 25 over 6. So that means if I do it down here, of course I have to fix it here as well. So divided by 6, so that would be 60 plus 25 would be 85 over 6 kilonewton meters. So I'm not going to give you the value because we're not really interested in MR. So I'm not going to give the decimal of MR. But we're interested in the location, right? So that would be MR over FR. MR was 85 over 6 kilonewton meters. FR, if we scroll up a little bit, was 5 kilonewton. So that gives me 17 over 6 meters, and that is 2.833 meters will be the location. So maybe we can just sketch that in here. Maybe we'll take green. So 2.8 would be just somewhere slightly past 2.5. We'd know this one would be R is equal to 5 kilonewton, and this distance would be 2.833 meters. And with that, we've taken this distributed load and we've created a concentrated load and found its location.